This is a video covering the architecture of my relay computer, and it forms part of a 2020 update series of videos, and this is a first in that set. Following this, there will be a video covering the instruction set of the computer, an assembly language based around that instruction set, and then an example of programming the computer from assembly language through to hand compiling into a list of instructions. Following that, then there'll also be a tour of the computer and then a demo of it operating. But for now, let's dive into the architecture. When discussing the architecture of this computer, it's worth realising that it's not the only one that uses this architecture. In fact, actually my computer has a direct parentage between two other computers. So mine's directly based off of a computer named the RC3, which was built by Phil Ryals and his team in the Museum of Computer Culture. And basically the architecture is exactly the same between the two computers, just there's a slight difference in scale here. So the Phil's computer on the right there is actually about the size of a fully grown man, whereas mine is about, well, maybe a third of the size. So they're very, very similar, but actually mine's definitely a miniature version of that computer. Now both mine and Phil's computer also have a direct parentage as well, and these all go back to the Dr. Harry Porter's computer. And again, this is where all the architecture started from here. So again, his is even bigger again, and definitely more spread out. But effectively, these are all the same computer and all work in very similar ways. So the architecture that you see in this video is used by all three computers. Now, if you're going back even further, you could say that that computer has a heritage with the Konrad Zuse computer. So there's Z3, which was made in wartime Germany in 1941. Certainly the adder part of the circuitry has a direct descendant from this computer. So there's quite a good heritage of relay-based computers. And of course, although these are nothing near as powerful as today's computers, they're still a fully fledged computer. So what is a computer? Well, really, it's something that computes things. And really, I guess that means that it's going to be manipulating data and numbers. So a very simple example is doing addition. We're adding two numbers together, and this is the sort of thing you'll have seen at school, no doubt. But what's actually behind this? It looks quite simple, but actually there's a bit going on. If we draw this in a slightly different form, you can see that really that each number is expressed as a series of ones, tens, hundreds, and then thousands, and so on. So really 124 is 4 ones plus 2 tens plus 1 100. That might seem obvious, but actually that really is what's behind it. You're summing up the numbers in each column and then carrying. So fine, okay, so that's how addition works. So the question is then, what do we need to do if we're going to have a computer that does this? Well, effectively we need to store each one of those digits. So to store the number 124, we actually need to store three values. We need to store a 1, store a 2, and store a 4. And for each of those numbers, what are the possible options? Well, there's 10 different options, the numbers 0 through to 9. So if we want to store the number 4, we have to set 4 for that particular number. And same for 2, same for 1. Now the question is, how can we store one of 10 different options in a computer? Now you could do it maybe by using voltage. So you could say, well, 1 volt is 1, 2 volts 2, and so on, all the way up to 10 volts. But the problem there is, how accurate is that going to be, and how reliable is it? And certainly there are computers that work that way. But on here, there is a better option that's more suited to working in electronics. So we've seen here that basically what we work in here so far is base 10. So we have 1s, 10s and 100s. But base 10 isn't the only numbering system. We could also use one called binary, which uses powers of 2. So 1, 2, 4, 8 and so on. And this is known as base 2. So turning to our example of the digits again, you can see that to store the number, say 213 at the bottom, we have to be able to store 10 different values. But in binary it's much easier, because values are just on or they're off. Now the binary works exactly the same as for the base 10, in that you can see the number at the bottom, the 1101010101. We're saying we want 11 plus 14 plus 116 plus 164 plus 128. Add all those together, you get 213. So they're both a direct representation of the same number, It's just that this one is much more suited to electronics because you can just make things that are on or off. Much simpler to handle. And that's basically it for numbers. So now let's talk about registers. So quite simply, a register is just a place to store a value. So in this computer we're using 8-bit values, as you can see there, because there's 8 bits in that value. That means that we can basically hold a number up to 256. Now of course you could go further, so you could have 16 bits, 32 bits, 64 bits and so on, and all you do is just keep adding more bulbs in this case, or just more bits. So given a register, the next thing we want to do is be able to get values in and out of that register, and this is where something called buses comes in. So basically each relay has a wire that runs through each of its bits, and that then means that you could add another register and connect it to the same bus of wires. So here you can see all the ones are connected together, the 2s, the 4s, the 8s, the 16s and so on. This then means if we had two registers A and B, we could select the value that's in register A onto the bus, and then we could load the other register from that, like so. Once that's done, you can then deselect register A, and now you've effectively copied the value in register A into register B. And that's basically all registers are. They just hold a value in them for later use. Now let's simplify this diagram a little bit, because we don't want to draw 8 lines between each and every part of the computer. What we can do is just draw it as a single white line to represent our bus. Let's simplify the diagram a little bit more. And we can see now we've just got register A and B. And again, these are 8-bit registers. We know they'll hold 8 bits and they'll connect to the 8-bit data bus. Additional to A and B then, we have registers C and D. So these are our first 4 general purpose registers. Now I say 4 general purpose registers, we actually have 8 in the computer. So here's the next 4, M1, M2, X and Y. And again, these work exactly the same, so we just now have 8 identical registers that we can use. Again, you could copy a value from A to M1, from X to C and so on. Now the M12 and XY registers do have a slightly special purpose though, so they're actually grouped together to form pairs of 8-bit registers. And what you can do then is you can use these together to form a larger 16-bit register. So in this case, M1 and M2 form the M register and X and Y form the XY register. Now what can we do with that 16-bit register? Well, it has its own bus, and we can gate the M register and the XY register onto that 16-bit address bus. So you could copy the value from M over to XY, and basically that will copy the value of M1 into X and M2 into Y. Now actually, there's a slight lie there. You can't load back into M on this computer. M is read-only. And now the reason for this will become apparent when we start looking at the instruction set, because we will be limited in how many different operations we can do. So just remember that the bus on the left is the data bus, and that's 8 bits wide, and the bus on the right is 16 bits wide. Right, so that's enough for registers. Let's take a look at the ALU. And this stands for the Arithmetic and Logic Unit. But let's think about the arithmetic side first. So let's just return to that example we saw earlier on. And on the right there you can see the base 2 binary equivalent. So this is exactly the same equivalent, so we could say that in register B we've loaded the value of 124 in there, and in register C we've loaded the value of 89. And what we really want to do is add them together and put the result into register A to get 213. So how would this work? Well, you just do it exactly the same as you do the decimal addition. So if we look at the first column on the right, we add 0 to 1 to get 1. We then add 0 and 0 together to get 0. We add 1 and 0 together to get 1. Then the next one, it gets a little bit more interesting because now we've got 1 and 1. So 1 plus 1 is 1, 0 in binary. So we take the 0 and we carry the 1. Now we have 1 carrying, 1 in B, 1 in C, which is 1, 1 in binary. So we put in the 1 and we carry the 1. We now have 1 in B and 0 in C and 1 in carry. So we have 1 plus 1 equals 0, carry 1. And again, now we have 1 carry, 1 in C, 1 in B, so that's 1, 1. So take the 1 and carry the 1. And there we go, there's a complete example. Now if we actually had a carry on the very last digit in this number, Well, that's fine because the ALU can cope with that, and it'll basically set a flag to say that there's a carry, and then we can decide what we want to do with that later on. So we've now got the result we wanted into register A. Now if we want to do something further with that, we can copy that value into register B, like so. And now we could load something into register C and do the add again, or in this case we'll use another one of the ALU's functions, which is the increment. So effectively we're just going to add 1 to the value. That's easy enough again. What it'll do is just set a carry in value on this. So all we're going to do is add 1 to the first bit of B, and that's it, that's an increment. Okay, so that's the arithmetic side of the ALU. What about a logic side? So if we do a very simple example first of all, and just concentrating on a bit at a time now, if we have a bit in register B that's off, the result will be that that bit will be set on, and vice versa. Slightly more interesting then is the AND logic function. So again, this now uses both registers, B and C, and for any bit of that, if both bits are off, the result is off. If either one of the bits are on, the result is still off. It's only on when both B and C have a bit set. Next up is OR. So again, this now works with if B or C have a bit set. Now this is interesting. This is where you get the sort of old programmer's joke of would you like tea or coffee? Yes. Now this is because actually computers tend to use the inclusive OR, which is what you're seeing here. So if you say yes, you mean yes, you would like tea and or coffee. Now in natural language you tend to use the exclusive OR, and we have a version of that here as well. So here you have tea or coffee, and likewise the XOR function will have either C is on, B is on, but never both at the same time. Well, let's work through an example of that then. So if we go back to an example here where we've got 124 in register B and 89 in register C, we can XOR the values together. And all we do is just go a bit at a time, so it's a bitwise operation, and just perform the truth table we just saw on each value. So you can see then that the light at the bottom only comes on if it's one value or the other, but not both. Something that's quite interesting with XOR in that if you took the value that's in register B and copied A over to it, so it's now holding 37, if you perform an XOR with 89 again, you actually get the original number you started with. So effectively XOR, if run twice with the same number, will give you back the original number you started with. And this can be useful in some cases. Right, so let's get back to the architecture diagram. So again, we'll just focus on registers A, B, C and D for the moment. If we look at the ALU, it's always directly connected to registers B and C. So whenever B and C changes its contents, the ALU will automatically update and calculate all the results available. You can then choose to gate that result back onto the data bus. Now from the data bus you could load it here into register A or register D, but you can't load it into register B or C, and that's down to the way the relays work electronically, is that actually that will cause a feedback loop and it will just clear the whole thing down. This is also why some computers tend to have an accumulator register where every time you do an addition it goes back into the A register and the A register itself feeds back into the ALU, but we can't do that here just because that's not the way relay computers work. It does then mean every time you do an add, if you wanted to keep on adding, you just got to keep copying the value from A back into B again. That's not all there is to the ALU, as I hinted earlier on. It also has 3 registers, and these are single bit registers. And what these do is every time there's an operation happening, it'll update these 3 condition statuses. So the one in the middle, CY, is the carry flag. So if the last arithmetic operation resulted in a carry, it'll set this flag. And we can use these later on to do interesting things. The Z flag is quite straightforward. That's set if all bits of the result were 0 or not 0. The sign flag is a little bit more interesting. Effectively that's set if the most significant bit, so bit 128, is set as a result of a calculation. Now this is called the sign bit, and typically it's used to tell whether we had a negative or a positive number. What's that? Well, the whole thing so far is we've been using unsigned numbers. So far we've been using numbers from 0 up to 256. But actually there is a way of storing negative numbers in a computer, and it's called 2's complement. So if we start with a value of 1, the way we calculate a 2's complement is first of all to not the result. So effectively that will set all bits on except for the one we originally had, and then you increment the value by 1. We now have a notional value of -1 here. And all this is technically about how you interpret these values, because you could look at that and also say, well, that's 255 basically. But another way of looking at it is it's -1. And it's all about the sign bit at the left as to whether it's a negative or positive number. Now the reason why this works is because if you add 1 to this, it will roll over to 0. So it's just a way of storing negative numbers, but it does mean then you get half the range as well. Right, so just let's go back to the complete diagram again that we've got so far. So far you can see we've got 8 general purpose registers, a data bus, an address bus, and we've got the ALU. So far really we've just got a glorified adding machine. You still have to operate this all by hand, but effectively you can do a certain amount of interesting instructions. So it's just like basically like a pocket calculator, just that it's not so small. And at the moment we're limited to be able to do 8 values, but that's not going to be very useful when we want to do more complicated calculations. So what we really need is some memory. So let's think about those registers again. So here we've got 2 registers, B and C, and notionally you could think of these as a memory because it'll hold on to 2 values. Effectively this is a 2-byte memory. 8 bits is notionally 1 byte. Let's simplify the diagram down a little bit. Now we can imagine that a memory, a 2-byte memory, would look like this. If we wanted to extend this to 4 bytes, we just double up on the number of registers. So now we have 4 registers to hold 4 bytes. If we times that by 4 again, we've now got a 16-byte memory. And you can see how the pattern follows here. Now the way we want to work with these is rather than calling them A, B, C or so on, we can give each one a number, a little bit like how you'd have house numbers. So if we start at the top left, we've got location 0, 1, 2, 3, 4, 5, 6 and 7. And continue on the right, we can go down 8, 9 and A, B, C, D and E and F. Well, this is hexadecimal notation. So this is a base 16 numbering system and it just works quite well when dealing with binary numbers, as 4 bits is always equivalent to 1 digit of hex. So in the case of a byte, you could store that into hex digits. And it's a nice short way of writing a binary number. So we'll be using them here. And the reason why is because you can see this is still a very, very small memory. What we want to do is make this bigger yet again. So there we go, we've now got a 64-byte memory. Now you can probably see now why you wouldn't want to do this with relays, because if you think each one of these would be a register card, I've got 64 of them to make this memory. And this is why it's not really feasible to do this in relays. Especially when you think about how much a modern memory chip would hold. You can start seeing how it gets ridiculous quite quickly. Now in this case, because we've got a 16-bit address bus, we can do 2 to the power of 16, and that means we've got 65,536 locations that we could address. Interestingly, this is why when you start getting 32 and 64-bit buses, the numbers start going up in orders of magnitude. Now address-wise is being addressed from 000 all the way up to FFFF. So again, this is the hex notation. Now in practice actually I've used 32K memory chips, so actually I'm only using the first 15 bits of the address bus, and the last bit is to tell it whether to activate the memory chip or not. The upper 32,000 locations then will be used for other things, so later on we could use screens or could use other peripherals to attach to the computer and then use those as a location and just address them like any other memory. It just happens that they have some sort of special function. So back to the architecture diagram, let's get the memory block added on. So we'll extend the buses down a little bit and bring our new memory block in. So the memory needs 2 inputs. It needs the address bus to tell it where to look in its memory, and then the data bus to actually bring the value in and out. And that's basically the memory pretty much complete. So we've now got really what is a glorified adding machine that's now got a lot of memory. So far it's not a computer. What we need to do now is add the ability for it to be able to run programs. Now programs are just a list of instructions that the computer needs to operate, and those instructions will be held in memory. But what we need is something to tell us where in memory the current instruction is at. And to do that we have a program counter. This is just simply a 16-bit register, and it will just hold on to that address location. Now every time we do a part of the program, every time we do a line of the code, we need to advance the program counter on. And as you can see, there's no way of getting to the ALU from here, so what we do is we have a custom 16-bit incrementer. And what this can do is this can add 1 to whatever value is on the address bus. Now this isn't quite the same as the adder that's in the ALU. The ALU is designed to add two numbers together, whereas this will only add one number and just increment it by one. More importantly, this is known as a half adder, so it's a much simpler circuit because it's only ever going to deal with one value plus one. The result of that incrementer then goes into the incrementer register before then going back onto the address bus. And the way the operation works is like this. The program counter will be gated onto the address bus, where it's picked up by the incrementer and the value is loaded into the incrementer register. So now the increment register holds the PC plus 1. And then we can put the incrementer value onto the address bus to load back into the program counter. And this is how every time you just keep adding 1 to the program counter to move it onto the next location in memory. So now we know where in memory to look for the instruction, we need to be able to load the instruction into the computer. And to do that, we just have another 8-bit register, this time one that can only be loaded from the data bus, it can't be read back onto the data bus. And all that will happen here is that when we want to load a line from the program, load that value into the instruction register and then we can operate it on from there. Okay, so we've nearly got our architecture diagram complete, but there's just one final thing missing, and it's the thing that makes it a true computer in every sense, and that's the ability to do branching. So let's open the diagram up because we're going to put one last block into here. And this time it's going to be a J register. So again, just a 16-bit register made up of two 8-bit registers, J1 and J2. And again, a little bit unusual and a bit specialised in that you can only load it from the data bus and you can only gate it onto the address bus. And the way this works is that when you want to do a jump to somewhere else in memory, so say if you've got an instruction that says, well, if the last operation was 0, then go somewhere else, the way this would work is you would load the location that you want to jump to into the J register. So you load it first by loading the upper 8 bits into J1, then the lower 8 bits into J2. And then if you decide to take the jump, so basically in this case if the Z flag was set in the LU, then you just gate J and load the program counter from J. And effectively now that's moved the program counter to somewhere else in memory, and effectively then you've taken a branch. And it's with the jump register that makes this a fully functioning computer that can do pretty much anything a modern computer can do as well, just a lot slower. And with that, we've got to the end. So here's the architecture diagram for the computer. So if you do have any questions, feel free to pop them in the comments below and I'll do my best to answer. Otherwise, it might be worth taking a look at the instruction video next. And that's basically the codes that will be loaded into the instruction register that tell the computer what to do and how to do it.